All right. It appears that I didn't cover a couple of slides in the lecture last Wednesday or Monday before the exam. And so I wanted to cover those slides here. They have to do with Speed Demon Granny and the relative velocities or different perspectives in this, as illustrated in this drawing. So we have three different perspectives. We have the cop, the law-abiding citizen, and Granny. And the idea is that we want to represent the relative velocities of certain objects with respect to the reference frame of another object. And so the definition that we work with is, we'll say VAB, this is a notation. We say that VAB is the velocity of A relative to B. So we imagine that B is the observer, and B is watching A, and A has a velocity VAB. So we can think of this as, in some absolute sense, as the velocity of A minus the velocity of B from some third vantage point. So given this definition, it's clear that if A is watching B, if we have the velocity of A with respect to B, that should be the negative of the velocity of B with respect to A. So looking at this drawing here, this sketch, VLC is the velocity of the law-abiding citizen with respect to the cop, and that will be 30 meters per second. And so if we look at the velocity of the cop with respect to the law-abiding citizen, it looks, according to the cop, as if according to L, it looks that the cop is moving to the left at minus 30 meters per second. So that relationship is represented in this equation here, that VAB is equal to minus VBA. So if you reverse the sign of A and B, you should get a minus sign. And we can think of this as being a vector, velocity vector, where the head of the vector is A, pointing to the object, and B is the tail, which is residing at the observer. So if we think about the velocity of Granny, we can see that this relationship will hold, that the velocity of L with respect to C plus the velocity of G with respect to L will give us the velocity of G with respect to C. And that's represented by this equation here, which is true in general. If we have VAB plus VBC, that gives us VAC. And so the idea is that you want to rearrange this, and you can rearrange, permute the A and B, keeping track the minus sign. And then whenever you have the B on the inside, you can basically replace it by what's left on the outside, the A and the C in this case. So there was a matrix demonstration, which I can't show you on this computer, unfortunately, because I don't have that software installed. But basically, it was showing what you can imagine seeing here, showing L moving to the right and G going faster. And then we can switch reference frames so that L is at rest. So this sort of, think of it, a helicopter that's hovering over L. And then in this frame, C would be moving backwards, G will still be moving forwards. And then in the third frame, reference frame, Granny's frame, basically Granny will be at rest, L will be moving to the left, and C will be moving even faster to the left. So these are the different reference frames, and the idea is that the laws of physics can describe all of these reference frames. So then we moved on to describe 2D relative motion. All of these equations are valid for vectors in 2 dimensions, and the example I wanted to give was that of rain falling straight down and a vehicle moving in the rain, and then trying to figure out the angle that the rain will hit the windshield according to the reference frame of the driver who's moving 30 meters per second. So the first thing you do is you put the numbers in and replace them by symbols. So we say that the velocity of the y direction has a magnitude of 10 meters per second and is pointing down. And then v sub x is going to be positive according to this definition here, and it's going to be 30 meters per second. Okay, so this is v sub c is the car is equal to v sub x in the x direction. V sub r, the velocity of the rain, is minus vy. This is a positive number in the y direction. So it's pointing in the minus y direction, that is down, and it has a magnitude of 10 meters per second. Okay, so now what we're interested in is the velocity of the rain relative to the car. So then we go back to that previous definition, right, this one, and we say that it's velocity of the rain minus the velocity of the car. So now we need to draw this as a vector. The velocity of the rain is pointing down, and then minus the velocity of car is pointing to the left with the same magnitude of v sub c. So here we have a right triangle, and what we're trying to figure out is this angle, theta. So we then need to, and that's a simplified drawing here, so the side of this triangle is v sub y. Now we're ignoring all the signs because we don't need them for the angle. And we have, this is v sub y, this is v sub x. And so we use the familiar formula that the tangent of this angle, theta, is the opposite divided by the adjacent. So the opposite happens to be v sub x, the adjacent is v sub y. So that happens to be this angle theta. And so theta is the tangent inverse of vx over vy. And that's how you solve this problem. So the last thing was a concept test. And in this example, we have a race between 3 swimmers all of whom can swim equally fast. And the goal is to reach the other bank of the river. So they don't actually have to land here, they just need to reach the other side. And the question is, which of these swimmers, they have different strategies. So swimmer A is going to swim against the flow of the river, which is moving horizontally. B is just going to go for it, go straight across, and doesn't care about this. And then swimmer C is going to try to go with the flow, take advantage of the flow, and then hopefully get to the other side faster. So the question is, who wins? Is it swimmer A, swimmer B, or swimmer C? Or is it a tie? Or have I not given enough information? So you can think about this, pause the video. Alright, we're back. And so let's think about the following. Okay, I didn't specify what the velocity of the river was. So we can make it anything we want. And presumably the answer maybe we need to know the exact velocity, but I don't think so. Let's assume the river is not flowing. Well, if it's not flowing, then it's clear that swimmer B is going to reach first, because the swimmer B has the velocity component that is maximized along this vertical direction, and it's the time that it takes is the distance d divided by the velocity along this vertical direction. All of these A and C, they have smaller components of their velocity along the vertical direction, so they're actually going to take longer to get to the other side. So then we can then add a velocity vector to all of these swimmers, and what we're doing is we're adding velocity along the horizontal direction. But that velocity along the horizontal direction does not change any component of the velocity along the vertical direction. And so it turns out that swimmer B, who on a calm day, well, if the river were not flowing, would have been the winner, will still be the winner even when the river is flowing. It doesn't matter how fast the river is flowing. It is irrelevant. It's true that the swimmer may go further downstream, but their strategy of swimming directly towards shore is the optimal one.